Hi everyone, thank you so much for joining. My name is Claudia, and if this is your first time here, we're HelioHub. We're a Discord community for undergrads and recent grads interested in heliophysics, and we're funded by the NASA Coffee's Drive Science Center. Um, I'm joined, as usual, by my lovely team, Dan, who works at the Space Sciences Lab in Berkeley, at UC Berkeley, and Phoebe, who's an incoming PhD student soon. And I'll pass it off to Phoebe to introduce our guests. But just for this webinar, if you guys have any questions, feel free to use the Q&A function instead of the chat, and we'll be monitoring that. Yeah, so I'll pass it off to Phoebe.
We'll have a dedicated session at the end for you guys to ask questions, but you have things throughout, you can put them in the Q&A and we'll catch them. So today joining us, we have Dr. Craig DeForest. Dr. DeForest leads the Department of Solar and Heliospheric Physics at SWRI, which is the Southwest Research Institute and the one located in Boulder, Colorado. He also served as the former chair of the American Astronomical Society's Solar Physics Division, SPD. He received his bachelor's degree studying physics at Reed College in 1989 and completed his PhD in applied physics at Stanford in 1996. Then, after graduation, he jumped right into his science career, which included working at a nuclear reactor and then conducting outreach for the SOHO mission. His interests are in studying the solar wind at the solar corona, scientific imaging, and magnetohydrodynamic modeling. He's also an advocate for open source scientific computing and has interest in lowering barriers to space through developing new infrastructure. He's the PI for the Polarimeter to unify the corona and heliosphere, which is known as the punch mission, which he will be telling us all about in today's solar circuit. So please welcome Dr. Craig DeForest.
Thank you, Phoebe. What a kind introduction. Glad to be here tonight to talk with you folks. Can you see my screen? Is that still up? Excellent. Okay. So we're going to talk a little bit about Punch, which is a little mission that we launched almost a year ago that has 4 spacecraft that are observing our environment in space. Now, when I give this talk to general audience, I do a little zoom out thing. Where I compare the scale of the stuff we're looking at to physical scales around us. I'm not going to do that here because there's too much other material, but the thing I like to remember is this is astrophysics at home. Punch is not a telescope that's looking at distant objects that will never affect you. It's looking at the solar wind and space weather, which wash over us right here at home on our planet. So with that, uh, what are we doing? Well, we're trying to unify solar physics with heliospheric physics. I've said that enough times now that it almost sounds cliche to me, but those have been two different disciplines for most of my career. Solar physics looks at the sun, it's a branch of astrophysics, and we've used remote sensing to view it. This is a series of images from the LASCO instrument on SOHO. Uh, which has been photographing the solar corona for almost 30 years. Uh, on the right, we have a typical data set from traditional heliospheric physics, which is a set of parameters sampled by a particular spacecraft, in this case ACE, uh, as the solar wind washed over that spacecraft. So on the left, we get a large global view of what's happening in the corona and the structure of it. On the right, we see everything there is to know about one point in space. And the parameters here are velocity and density and temperature and the magnetic field, all 3 components of it. There are many more, but they're all identified at a single point in space as the solar wind washes over it. And so I like to say if you want to study the large scale structure and all you have is these in situ probes, it's like trying to learn about human anatomy if the only tool you have is an electron microscope. Likewise, if you try to understand the microphysics of how plasmas operate and all you have is the LASCO imagery, it's like trying to do cellular biology when all you have is a scalpel. Uh, so right now we have Parker Solar Probe, as you probably know, flying through the solar corona every 3 months or so, 4 months, uh, sampling the material there. And so it's bringing that material inward to the corona. Punch is the inverse. We're bringing that global picture out into the solar wind that fills the solar system. We're trying to image these structures by the faint glimmers of sunlight that reflect off of them. So we're imaging Thomson scattered light. That's light reflected by free electrons in interplanetary space. All this stuff that you're seeing in the LASCO imagery over here on the left is just that. It's light that's been scattered by free electrons. The protons come along with them, but they don't scatter nearly as much sunlight, so we don't see them. All right, so we have 4 spacecraft. We're trying to understand the corona and the heliosphere and solar wind as a single unified system. We're doing it by imaging them in 3 dimensions all the time. We're making polarized images of Thomson scattered light. We have 4 satellites to do it. I'll tell you why shortly. And it looks like I have an out-of-date slide. We are not in phase D. We are in phase E. We are operating. We've been operating for almost a year. So sorry that that has a little bit of a zombie label. So this is just a view of the different scales that are important. That's the sun. As we zoom out to a 90-degree field of view, we have the problem that the sun is tiny. So this movie I produced in polar coordinates so that we could see the scale of the planets and the solar system together with the sun itself. So in polar coordinates, you can see over on the right, that's the ultraviolet corona. The orange stuff here is what you might think of as the normal corona you might see during an eclipse or in a coronagraph. And then out the gray stuff to the left is the solar wind. This movie is kind of old now. We made it with the stereo mission, but this shows a solar storm, a big system of magnetic field and material forming in the corona and being launched out into space, sweeping over Venus and ultimately impacting the Earth. And the dial there is being driven by the ACE spacecraft. And so as the density wave from the corona washes over the spacecraft, you can see that it actually senses the material. We'll just let it hit the Earth one more time here. So this is spanning 90 degrees of field of view, but the scale is logarithmic. That's so you can fit everything in one place. So Punch is doing that now routinely and all the way around the sun. This is an early image that we released last May from Punch, and it's a composite. That dashed circle that you see near the center is the outer limits of the LASCO field of view. That's as far out from the sun as we've been able to routinely image the solar wind ever since we knew that there was solar wind. Punch is going out to 45 degrees. So you're looking at a 90-degree field of view here. That's from the zenith down to the horizon. So it's an enormous field of view. You can see various familiar constellations here. And you can tell that it was taken in late May or early June because Orion is right next to the sun, which is in Taurus. So that's your little bit of astrology for the day. We'll come back to movies like this in a minute, but I just want you to see what the Punch data are like. They are better than this now, and they will get much better. Let's see, here's our science. We're looking at these 6 topics, but it boils down to 2 objectives. How does the corona become the solar wind, which streams out at 1,000,000 miles an hour all the time, all over the solar system? And we want to understand the dynamic evolution of the transient structures, the space weather, if you will, in that material. So the first 3 topics are all about the ambient solar wind. These are data that we had before we launched Punch from stereo, just showing that the outer solar corona, surprisingly, is every bit as structured as the inner solar corona. So if you've seen those beautiful ultraviolet movies, you know that the atmosphere of the sun is extraordinarily complicated. It turns out the outer corona is too, and we didn't know that until pretty recently because there's an interplay between the noise level in an image and how much detail you can see in that image. So coronagraphs that looked at the outer corona, like LASCO, seem to have much higher resolution than they do. The stars in LASCO images are just a pixel or 2 wide, but the smallest feature you can see is dozens of pixels wide. And so we didn't realize until quite late in the game just how structured the outer corona is. This is what you get if you take that movie and remove the average brightness over a 2-hour window. You can see that not only is the corona structured with that wood grain striation, the radial structure, it's also a riotous torrent, we called it, of blobs and streams coming out in all directions all the time. These data can't alone tell you that the corona is all local ejecta, but they're consistent with that view. So we learn in our Phil Sci class, philosophy of science, that um, science is all about falsifying hypotheses. These data can't falsify the idea that the corona has no smooth background, that it's all ejecta. We can use that motion to measure the solar wind speed, and we're just starting to do that now. I'm not going to dwell on it, but we don't have routine measurements of the speed of the solar wind as it leaves the sun. And by tracking features like this with punch, we will have that very shortly. In the outer parts, this is right square in the middle of well, it's not the middle, it's the inner part of the punch field of view. We can actually see the end of the corona itself and the beginning of the turbulent solar wind that fills the solar system. Again, these are data that came from stereo before we launched punch. We're bringing the punch data up to this quality, but we're not quite there yet. We're looking at the Alphane zone. You may have heard about Parker Solar Probe diving into the corona itself. That's the area where the flow of the solar wind is not as fast as the wave speed. That's very important because, if you leave the room you're in, how does the air know to fill the void where you used to be? It knows because of sound waves. That's how the air communicates with itself where to go next. The corona is no different, and it uses various wave modes. The fast magnetohydrodynamic mode is something some of you know about, others will learn. It goes faster than conventional sound, and it travels at a speed called the Alphane speed. And the solar wind is not only supersonic, it's super alphanic. It goes faster than the fastest waves that propagate through the corona, or fastest mechanical waves. So as long as the outflow is going slower than that speed, it can communicate its motion elsewhere in the corona. You can see that when a CME leaves the sun's corona, the entire corona will respond. But once it passes through this imaginary surface, it can't communicate with the sun anymore. It's well and truly separated. Understanding the physics of that surface is really important. And Parker Solar Probe is studying it locally now, and Punch is about to give us data on its global structure. Very excited about that. There are 3 more topics having to do with transient structures. Basically, we'd like to understand CMEs. This is a Lasco movie of a CME leaving the sun, coming right at us. If you're old like me, you've watched an episode of Star Trek called Balance of Terror, where they discover the Romulans and the Romulans fire a weapon at them. And you can tell that it's coming right at the Enterprise because it just gets bigger and bigger in the field of view. Uh, CMEs are like that. And this one was coming right at the Earth. But we can't identify where it is in 3 dimensions just from this 2-dimensional image plane. So by using polarization properties of the scattered light, we can measure the 3D structure of CMEs. And I won't dwell on it because I want to keep moving, but this is a very important aspect of what we will be accomplishing with Punch in the months to come. CMEs are very complicated. This is a really well-presented CME that we saw with stereo. And actually, you can see if you've studied different parts, these large clouds of material go sweeping through the solar system, and they sweep up solar wind. So you get a density front on the front of them, and we can actually see that in the imagery. It's phenomenal. And then inside, you can see remnants of the magnetic structure that gave rise to the CME in the first place. That's that erupting writhed core. It's like a rubber band that's been twisted up so much that it forms little knots. It's writhing. And then a complex interior that's hard to sort out with this 2-dimensional image. But by imaging all this in 3 dimensions with polarization, we hope to sort out this kind of structure. Uh, I could talk for an hour about space weather. Space weather is the suite of phenomena that happen when particles or clouds of material from the sun sweep over the Earth. And it's important, it affects our environment, and it's the thrust of a lot of research. So, Punch has an application which is helping to learn how to forecast space weather. Uh, this is a movie I love to show because it's one of the least seen movies to come out of the stereo mission. This is a co-rotating interaction region in the solar wind, and Punch will have a great view of these. In fact, we've already seen some in the data. Uh, but these were first identified in situ. This is a place where, because the sun is rotating, fast solar wind that happens to be going quickly uh, can overtake slow solar wind that came from a different part of the sun, and it forms a pile-up region where it all compresses. That's this purple line here in the cartoon. What you're seeing here is not looking down like the cartoon. You're looking through the solar system. You're looking sort of edge on this thing. This was a view that nobody had ever seen before, and now, of course, we're seeing it routinely with Punch. So the mission. We want to image these large structures in the solar wind. They're very faint. These are plots of brightnesses of various things compared to distance from the sun. Remember, your eye sees angle, not position. That's why you can, crush somebody's head with your fingers. Um, so 1 degree is about the size of your thumb at arm's length. If you hold your arm out now and look at your thumb, your thumbnail subtends about 1 degree. 10 degrees is about the width of a fist held at arm's length. Uh, Desert sky, mountaintop sky, these are things from the Earth. And then the green light is the K corona, or the Thomson scattered light we're interested in seeing. And it rapidly becomes much fainter than all these other things. This is the Punch field of view here in yellow. And you can see that in this range, we're looking at things that are not only fainter than the sky, they're fainter than the zodiacal light, the dust cloud that orbits the sun where we live. They're fainter than the galaxy. They're fainter than the average brightness of stars outside the galaxy. So we have to work extraordinarily hard to remove all of these sources of light to see what we're seeing. It's about 3 orders of magnitude. So 99.9% of the light gets removed from Punch images in the outer field. Furthermore, the contrast is too great. There's 3 orders of magnitude or 4 orders of magnitude of contrast across this field of view. So we had to divide it into 2 instruments, a narrow field imager, that's a coronagraph, and a wide field imager that looks all the way out to 45 degrees from the sun. These are those 2 instruments. On the left, we have a coronagraph, the NFI. I'm sorry about the color of the labels here. I'm not sure what happened to that. That is I almost hesitate to call it a telescope. It's a telescope that's about as powerful as one of the binoculars in a pair of binoculars. But it has a very, very dark baffle system in the front and a small occulter that hides the sun from the camera. On the right, we have a wide field imager that's extraordinarily deeply baffled that can look out 45 degrees from the sun. Now, we had a problem that we had to get these instruments close to the ground systems so that we could downlink the images by radio. We collect a lot of images. When we did that, we found out that there's a giant planet in the way, the Earth itself. So we spread out 3 wide field imagers around the planet so that we could look outward in all directions. That's why there's 4 separate spacecraft. We built NFI onto its own spacecraft because it was easier to build 4 identical spacecraft and bolt a different instrument to one than to build a custom spacecraft that could carry a Wi-Fi and the narrow field imager. This is what the field of view looks like. So we take all 4 of those instruments, and this is a simulation, by the way, should be obvious. We get them in their orbits. Each field of view intersects the fields of view of the other 3 so that we can cross-calibrate. And as they go around, they fill in a large circular field of view over the course of their orbit. So they all work together. To do that, we synchronize each of them to within 1 second. Uh, they all operate once every 4 minutes. These jumps in position are to match the roll angle of the spacecraft as it goes around in its orbit, and that's every 8 minutes. So we take two full polarized data sets in each position, and then every 8 minutes we roll all four spacecraft together and then start the next observing window. To make this work, we have to have photometry that's better than 0.1% relative precision across all 9 million active pixels. That's hard. We'd like to achieve alignment to within 0.03 pixel everywhere. We're not there yet. We're at about 0.1 pixel. That meets requirements, but the 0.03 is a desirement, and I think we'll get there. This is our field of view compared to houses and things with an eclipse going on in the background, just to give you a sense of how enormous this is. We're really not looking at something that's far away. We're looking at things that are sweeping over us. All right, how do we get there? There are a lot of steps. I'm not going to dwell on all of them, but I'm going to give you a tour through what we did to the prototype data to get there, just to give you a sense of where we are. So to remind you, this is how bright things are. This is a set of images from the stereo High 2 instrument. These are 2-hour exposures of the star field. The instrument's in Earth's orbit looking back toward the Earth and Venus. So that's Earth on the left, Venus on the right. The sun's over to the right, just about where the cursor is now, on the right-hand side of the scale bar. If you have some alacrity, you'll notice the constellation Pisces up here. And this is the zodiacal light I talked about. It's the dust cloud that orbits the sun. And these vertical stripes are places where the planets are so bright that they're causing electrons to spill across the actual detector, the chip itself. So they make these vertical artifacts. And this dark thing on the left is an occulter that was designed to obscure the Earth from view. It did when the Earth was closer, but when it got this far away, it missed. All right, so the first thing we do is we take each pixel, we remove the faintest value of it. That allows us to get rid of the F corona, which doesn't change very much. And now you can see there's a little bit of stuff here. There's some solar activity on the right, a CME that comes out. You just barely see it. You can also see that the planets have a little halo of stray light around them. That's real. You can also see lots of stars. I almost forgot to point out, look at these scale bars. This is counts per second per pixel over a 2-hour exposure. So this is 0 to 30. When we remove the F corona and zoom in, we go 0 to 1. That's why there are so many more stars visible there. To get rid of the star field and see what's behind it, we freeze the stars. So now the images are resampled so that the stars are approximately fixed. And we can do the same trick. We find the faintest value of a given pixel in this coordinate system and subtract that. Now we're cooking with gas. We've removed most of the star field, and you can see that there really is something moving across here. At this scale, from 0 to 0.1 counts, so 0.3% of the original dynamic range, you can see things like the misalignment of the dust cloud as it moves from top to bottom. That's because stereo isn't orbiting exactly in the plane of the ecliptic. It's a little bit out. And so as it orbits, the F corona moves in the image plane. You can also see little trails left. Those are statistical artifacts of stars as they pass through. Well, we can remove that by now fitting each pixel with a cubic. We do that and we get this. And there's still some artifacts that we couldn't quite get rid of this way. So we applied a motion filter. We know that the solar wind is moving, and we can use a neat effect using the Fourier transform to isolate things that are not moving and thereby remove them. So we did that here. Now you can see these wispy structures of the solar wind itself, but look at the dynamic range. It's 0 to 0.03 counts per second over these 2-hour exposures. So we're looking at 0.1% of the dynamic range. Punch data reduction is similar. We do the same steps, but we have to do more. And so that's why I'm showing you this sample prior mission instead of the punch process itself. Um, One of the things we had to do with punch is we have multiple instruments that are being combined into one virtual instrument. So we had a problem with something called coma in the telescopes. If you've ever used a telescope, you know that near the edge of the field of view, stars tend to get a little smeared out. It turns out that's been a problem for a long time. The earliest reference I could find was this Kepler Galilean Peña paper from 1611. I used Google Translate to get the Latin into English. And they're grousing about how stars turn into basically comets on the edge of the field of view. So we use the Fourier transform and something called the convolution theorem to convert the point spread function of our telescope to a completely standard and uniform one. And this is an example of that happening. These are actual images of stars that we took before launch. We took the engineering model wide field imager out into the high desert and took pictures of the stars. And those are what they really look like through the instrument. But after we do this step of processing, the stars look absolutely uniform. This is an example of one of several things that we had to do that just to regularize the data so that we could merge them all together. Incidentally, if you have a modern stereo, that does almost the same thing. Like if you buy a Sonos stereo kit, those aren't very good stereos by the standards of people from the 1970s. The case is not built solidly, and the sound reproduction all by itself has a lot of distortion in it. But when you set up your Sonos, you hold up a phone next to it and you play a controlled sound into the phone, and the Sonos loads that and produces a giant matrix operation and inverts the matrix, and all of a sudden the sound is perfect. So it's very similar. It's analogous to what we're doing here, not with sound, but with images. We're taking a flawed system, and instead of heroically trying to make the system perfect, not possible, we fix it in post. All right, so analysis, the reason we use polarization is the amount of polarization of the light that we see, that faint remnant coming from the solar wind, tells us where it is in 3 dimensions. Here's how. What you're seeing when you see those wisps of solar wind is scattered light from the sun. Sunlight comes out. You've already learned that light is an oscillating electromagnetic wave, so there's an electric field. If there's an electron sitting in space, it shakes and re-radiates like a radio antenna. But the electron motion gets projected by the cosine of this scattering angle, chi. The intensity of the scattered light is, light is a transverse wave. So the component of this initial excitation that's along the new direction of propagation doesn't actually contribute. So that's where the cosine comes in. So that one polarization component is reduced by a factor of cosine squared because intensity is the square of the electric field. So by measuring the amount of polarization over here, polarization ratio, we can measure the angle out of the sky. That's this C angle. We directly measure chi, that's this angle I'm circling now, but that's that and the elongation from the sun, which is just where it is in the image plane, tells you how far out of the sky plane that feature is. Once we've solved this triangle, we know right where the feature is in 3 dimensions. That's why we use polarization. It works. I'm going to show you some baby pictures. So this is what the narrow field imager looked like when it was under construction. This is the actual flight hardware. And in the middle there, you can see a very complicated structure. That's the occulter, which is designed to minimize Fresnel diffraction around the occulter and into the optics. Over on the right, this is that system being tested in a solar simulator. It's in a vacuum right there, with a fake solar beam being shown on it so that we can measure just how dark the image is. This is the same system just before it got shipped to Southwest. This is the wide field imager. This is just one of the 3. There it is closed. Here it is with the door not yet on. And you can see these veins in the front are designed to minimize diffraction, and then they form an artificial horizon for the instrument. And then these very thick veins in the middle are to reduce glint off of the spacecraft itself. And then there's the lens in the back. So on the front, this thing is exposed to the eternal noontime of space, and down in the back, it's more than 100 times darker than the darkest desert night on Earth. Uh, really phenomenal. This is what that system looks like in our clean room as it's integrated into a punch spacecraft. There's a technician standing next to it. And this is what the technicians look like seen through the spacecraft. So this image is it's one of the first images taken by Punch, and it was taken in the clean room. And the reason I'm showing you this is to drive home that this is not a telescope. This is a wide field camera that is perfectly capable of capturing ordinary scenes here on Earth. This is one of the Wifis. This is Wi-Fi 1, I think, going into the same vacuum chamber to be tested. And over on the right is just an image showing that it's reducing stray light by a factor of 10 to the minus 16. So that's a lot of zeros. These are optics. If you've ever used a telescope, you've probably looked through a Nagler eyepiece. That's a special kind of imaging optic that's used. Well, the eyepieces are imaging optics that you use to look through the telescope by re-imaging a real image of the night sky. If you turn an eyepiece around backward, it takes the night sky and produces a real image. And so we got Al Nagler, who designed the famous Nagler eyepiece, to design our optics. They work great. That's a space qualified camera behind the lens tube there. These are the spacecraft being shaken at the top to make sure they'll survive, and down below they're in a thermal vacuum chamber to make sure they'll survive the hot and cold temperatures in space. This is all 4 spacecraft packaged in crates, ready to be shipped to California, and this is about 2/3 of the team that built them. Pretty exciting. Once we got them out to California, we unpacked them into a clean room at Vandenberg Space Force Base and mounted them on a Falcon 9 rocket. So these are, you can see 2 of the Wi-Fi spacecraft there and the UNify spacecraft over here. The other Wi-Fi is behind the adapter here, and that's the SphereX spacecraft up above. That's a different mission that launched with us. And the stuff in the back is the shroud that's just about to be sealed around all this stuff. Shortly thereafter, somebody took this picture. You're not allowed to take pictures on Vandenberg Space Force Base, but there's a train line that goes right down the coast. And one of the passengers on that train took a picture of our rocket or our payload as it was being transported to the launch pad. So that's a picture of Punch on its way at dawn. Just about a day later, these images came from the rocket itself. These are movies taken over Madagascar, just off the coast of Africa, on March 12th, right after launch. They ejected from the rocket at a walking pace from a little spring deployer. You can see them going out. And in about 120 days, they were 2/3 of the way, well, a third of the way, excuse me, around the world and spread out all the way around into that triangle to make the trefoil images you see. These are the results. So what you're seeing here is sort of is preliminary data that we released back in November. You can download images like this now, showing just what we see. And this is a pretty phenomenal data set. What you're looking at is minimally processed. You can see that we didn't yet have the flat field of the cameras sighted in. So you can see the seams as the constellation goes round. You're seeing images of the corona from the C-core coronagraph. UNify is still being worked on. But there happens to be another coronagraph handy, so we just threw that in there. And the outer part is all the wide field imagers. That is the moon going by there, that brightest thing. Counting in toward the sun, this is Mercury, this is Mars, This is Venus over here. Now, these planets are often seen in a line, and one of the things that strikes me during an eclipse, every one I go to, is that you can see the plane of the ecliptic. All the planets are going around, and there are very few other times that you can see that on Earth because the planets are all spread out, half at sunrise, half at sunset. Uh, Up here, you've got a comet. That's Comet Lemon going by. You can see solar material leaving and crossing the solar system at 1 to 2 million miles an hour all the time. Lots of CMEs coming out. When a CME washes over the comet, here comes another one. It will just, oh, that was the second one. Watch the comet. Uh, when a CME hits it, you'll see the tail of the comet respond. That sort of drives home that, yeah, everything in the solar system is affected by the solar wind, including this handy test particle that happens to be visiting. If you look uh, up over the North Pole here of the sun, you'll see lots of streaks. Those images are taken when the spacecraft are over the North Pole of the Earth, and they're looking downward because it's getting on toward late fall. They're looking downward to the south, and so they look through the shell of the Starlink constellation. Those are almost all Starlink satellites going by. And then, of course, in the backdrop, you can see the grandeur of the cosmos as the Milky Way comes into view. That left to right motion is our orbital motion around the sun, right? We're keeping the field of view focused on the sun, but we orbit about 1 degree per day, and so that's the rate that the sun is moving across the cosmos. Uh, I like to talk to this for a long time because it's a very rich data set. It's fun to see, and it gives me anyway a sense of place, right? Not only are we studying pretty fantastical things, the solar wind itself and these large features, we're studying things that are happening right here where we live. This is astrophysics at home. And I'm always reminded of our sense of place. This is where we live in the cosmos. So data refinement is ongoing. These seams are getting better. I'll show you some examples in a minute. We've already had some bonus science, which you might be interested in. I mentioned that comet. Here's a close-up of it at the lower left as the solar wind sweeps over it. In the upper right, this was sort of, whoops, my computer can only run one of these at a time. In the upper right, Swan is a comet that was discovered on September 11th this year. We looked through the archival punch data and it turned out we'd been viewing it ever since August, early August. So we just made this tracked movie of it. That's kind of neat. You can see it going by Mars there, and there's Spica moving by, and then Mars. And then if you look down below, there's somebody else photobombing here. That is 3I Atlas. So we captured 3I Atlas as it crossed through the punch field of view, and we're doing some science based on it now. It turns out we can actually track it at a time when nobody else could, because it's very hard to see faint things close to the sun unless you have something like a wide field imager. So lots of science being done there. Going forward, the spacecraft are working. We're collecting polarized images. This is a little piece of that same movie, only I've encoded polarization in sort of a standard way so that you can see how polarized the corona is. Hue, the particular color, encodes the direction of polarization. Saturation is encoding the amount of polarization. The stars aren't polarized at all, really, which is why they look gray. But the corona is polarized, and these CMEs in particular, as they come out, you can see in this direction they're magenta. They are strongly polarized. We can use that to locate them in 3D. We have to get a little bit farther into the data for that to happen. We're still combating various artifacts and getting the calibration sighted in just right. Fortunately, we're on the cusp of releasing another version of the data. Right now, the process data come in versions. The version 0 with a letter of the alphabet next to it, and we're about to release J, the 10th iteration. So on the left, you can see what we've been using to generate the movies like you just saw. On the right, you can see some sample data, just test data using the new pipeline. And what I want you to see is just how much more stable both the stars and the background nebulosity, or F corona, are in the new data. We've improved the photometry by about an order of magnitude, between a factor of between 10 and 30. Uh, the stars are co-aligned to within a tenth of a pixel now instead of a third of a pixel. Uh, and we're rejecting cosmic rays better. It's going to be spectacular. This is the same movie, but now with uh, F corona subtraction applied. So what you're seeing is uh, the corona itself out to about 80 solar radii. Uh, and then the stars are still there, they're in the way. Uh, but with the new, more stable imaging, we'll be able to remove them just like we did for stereo. So stay tuned and pull down some data if you want. These are all freely available. The J haven't been published yet, but as soon as we start making the actual data products instead of these preliminary tests, we'll be pushing them out the door too. Uh, let's see. This is a little weird. It took me back to the beginning of the slide set. And I could have sworn I had something more on engaging with punch, but huh, I think we'll just loop through the slide one more time. Uh, there's a slide missing, which is our website. We have a website, punch.space.swri.edu. If you go there, you'll see science nuggets, you'll see links to our data, you'll see links to our upcoming meetings. The next meeting we have is online, and it's on the 5th of March. You can get to it from the website. And we'll be talking about how to analyze these data, how to pull them down with Python tools, and how to manipulate them. We have an in-person meeting here in Boulder, Colorado in mid-May, May 12, 13, and 14. We'll also be streaming it live out over the internet so you can see the talks. So please engage. Come look at our data and join our team. Thanks.
Thank you so much. Yeah, there's the link in the chat for you guys if you want to click it and have
Sorry
it
for the snafu
there.
with the slides there, but thank you for putting that in the chat.
Mhm. We don't currently have any questions in the Q&A, but if you guys have some questions, you can unmute and ask them, or if you want to drop them in the Q&A.
Yeah, I was going to say, you can just raise your hand too and ask a question. At this point, you don't need the Q&A anymore. Just raise your hand. Or yeah, you can drop it in chat if you want to ask. I think you can do anonymously too in Q&A if you want. Absolutely spectacular imagery. I'm just floored by what we're seeing, and you're saying it's just going to get better and better, huh, as you continue to process.
So the process data that you're seeing there, about 1% of the light. So we have another factor of 10 to 30 to go in terms of light that we remove. We're at a place now where we have to mix in a little bit of star field because otherwise you lose the context. So for things that we show out to the public, we'll mix in a little bit of star field again.
Okay. Can you say more about your team? Because here at Space Sciences Lab, we'll build the instruments and often we'll do mission design, but we don't typically, except for a few cases, build the spacecraft and of some of these other things. It looks like you have all those capabilities at SWRI, and I'm just wondering, is that typical, or was Punch an isolated case?
Punch was the first of several missions that have now been built soup to nuts at our facility in San Antonio. We built the Cygnus constellation down there a couple of years earlier. Those really are, we called them large CubeSats. It was a CubeSat design with a slightly different mechanical form factor. Punch has fully functional three-axis stabilized bus, and that's something we can do now. So we're building those routinely, but we don't do that here in the Boulder office. So Southwest Research has about 2,000 employees. We have 2,500, I guess. Most of them are based in Texas, and about 100 of them are based up here in Boulder, Colorado, which is where I'm sitting right now.
Fantastic. Okay, I didn't realize. That's great. Any internships for undergrad since that's our
We
main?
do. There's a
Yeah.
student program. We have space science going on in San Antonio, punch co-Is in both locations. Uh, and we also work with the University of Colorado REU program to take
Okay.
REU students in the summer. That's going on right now. So the deadline is, if not passed, it's imminent.
I think
So
it
we're
passed.
looking at,
It
yeah.
passed on the 28th of January, I think. But
Ah,
that's where Phoebe comes from, and I think she saw you in the offices there at one time. She
that's
told me.
right.
Yeah, that's where we originally met.
That's right. That's
Mhm.
right. I remember that.
That's
So
great.
we've been taking 1 to 2 REU students for punch each summer, and we typically take 2 or 3 more for the rest of the division here in Boulder. Down in San Antonio, they work with a couple of dozen students a year that spread out across the divisions.
Okay. Well, if you have anything you ever want to advertise, we have over 200 participants in our HelioHub, and then I run another thing called Space Ops, which is a little more engineering focused, but just send things our way and we'll get the word out for sure.
Thank you.
Yeah, yeah, no, happy to do that. There's an eager audience out there. I haven't, I'm sure Phoebe and Claudia have some questions, and please, if our audience, if you have questions, just raise your hand. But there was something I was confused by. Every time we kept seeing the moon go by in that early data set, it was always on the left, and I had trouble figuring out why is
It's
that the
just
case?
where we cut the movie.
Yeah.
It goes around, it comes in on one side and goes out the other every time. And if you look closely in that movie, it does a little loop-de-loop in the coronagraph field of view. That's
Okay.
because we're using the C-core coronagraph, which is in a geostationary orbit. So it has a lot of weird parallax with the moon as it goes around every month. Uh, Punch is essentially fixed in that frame because we're in low Earth orbit. So there's a little, you see, the moon wiggles a little bit from the parallax, but not very much.
Okay. Okay. Looks like Phoebe or Claudia, we have a question in the chat. I don't know from Leah if she wants to ask it outright, or we could just read it for you. Somebody want to read it?
I'm not seeing it.
Oh, in the chat here.
I don't know if it was sent
I can read it.
direct.
Oh, I don't see
Yes.
it.
Oh, direct. Oh, yeah, yeah, yeah. I have to change that. Here, I'll ask the question for Leah. It says, what is one of the biggest questions about the sun that you hope will be answered with research using this data? Great question.
That is wonderful. I am hoping to understand what, personally, what is the origin of the variability we see in the solar wind at the Earth? If you stick a probe in the solar wind and allow it to wash over, uh, you'll see that it's extremely variable. Going back, in fact, I will share. I happen to have a plot, right? The one that I showed you. Uh, Boop, boop, boo. Where are we? Here. This plot has lots of little wiggles in it. And I used to think that was noise. That's not noise. That's the actual solar wind changing. There are little gusts and bursts of stuff that happen on all time scales, right down to the kinetic scale where it ceases to act like a fluid and starts to act like a bunch of particles. Uh, why is that? Well, when we have wind here in our atmosphere, it's always turbulent, right? There's essentially no wind that's just laminar. Uh, and so one might expect that that variation is turbulence because there are different streams interacting in this really violent hypersonic flow. Uh, but there's a lot of evidence that at least some of those are preserved structures that came all the way across the solar system intact from the corona, where you have some knot of magnetic material that's released by processes as yet not fully described in the corona. And it remains there in fossilized form for the 3 or 4 days that it takes to wash over the Earth. Uh, that's pretty exciting, right? What's the balance of that? Is that stuff that's coming from the star itself, or is it stuff that's developing in transit? Uh, and it doesn't have the same application that understanding the propagation of a CME might have, but it's of extraordinary interest from the standpoint of understanding how plasmas work.
Again, I have a follow-up question. A CME, especially one that doesn't encounter a planet, does it eventually fizzle out before it reaches the end of the heliosphere, or will it just keep going, 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 going?
Eventually they reach the end of the heliosphere. I don't have the slide handy, but you can demonstrate what happens if you own a sink. How many among us have a sink, right? We all have sinks. So if you um, if you turn on your sink and water flows down into the basin and it's a flat bottom, what you'll get is a disk of water that's going out really rapidly and then a wall that's stationary. And that's a great example of a stationary shock. The water that's spreading out across the bottom of the sink is going faster than the speed of ripples in the water. So it's arriving before there, it's like that Alfvén surface I talked about. Information can't get across the stream and back up, so the water can't actually move in. So it piles up at a shock, a wall of water, where the propagation speed drops below the sound speed. So that actually happens to the solar wind in the outer solar system. The uh, the uh, the wind gradually slows down for many reasons, and also ultimately impacts the interstellar medium, and there's a shock there. So a CME could, in principle, and in fact probably does, go all the way there and just slams into that shock and gets all stirred up. Uh, it, there is, as with anything, there's a lot more to the physics of CMEs than first meets the eye. We think of them
Right.
as clouds of material and magnetic field leaving the sun.
Right.
But one of the problems with having an Alfvén surface is that once a magnetic field line, remember in a plasma, field lines have sort of a semi-reality. Uh, they mean something. Uh, when a field line crosses through that surface, you get a loop going through, it can't retract. And so over time, as CMEs come out, the field lines pile up on that surface and they're stuck there. They can't come back in. Uh, but we know, right? Think back to your E&M class. The more field lines there are on a surface, the stronger the field is. So why isn't the magnetic field in interplanetary space really, really strong, right? The whole solar system should be really strongly magnetized because all these field lines have been piling up on the surface. They can't retract. There's physics going on in the corona that prevents that from happening. And every once in a while, you get a U-shaped loop that emerges out. But all of those loops and U-shaped loops go out and they pile up at the interplanetary shock. And of course, none of the field lines ever ends. They just get tangled up and reconnect, and eventually all that dissipates into a kind of magnetic froth. Uh,
Fascinating. Wow. I've never heard it put that way. That's fantastic. We have another question from Leia. You want to ask it? Oh, no, she's clapping. Okay. All right. This is a rare opportunity. Oh, here. Yes. Okay. Allison, do you want to go ahead and ask your question?
Hi, I just want to say, first of all, thank you so much for giving this presentation to us. This has been so fascinating. Um, so I've just kind of been wondering, like, what would be the next step for Punch? Like, can the system scale up? Like, is your goal just to collect more data, or
so
I
right
guess like,
now,
oh yeah.
oh, go ahead.
Oh no, I was just gonna ramble on some more.
Funny, me too. Uh, right now, our goal is to get the data in as good a shape as they can be, and they're far from that. It turns out this is harder than it was for stereo, and it's harder partly because we chose to do this with four separate instruments, and partly because we're collecting a lot more data. We've already downlinked over 1.2 million images from space. And so when we reprocess the data, it takes a long time to do that. And that's okay, right? We planned for that. But it also makes it cumbersome to make small shifts and iterate. And we knew that this would be an iterative process, but it takes longer than it did for stereo. I pulled about 2 months of all-nighters with one colleague, Tim Howard, and we generated a prototype pipeline for stereo that led to that slideshow I showed you. Doing the same thing for Punch, we have a team of 6 people who've been working on it for 8 months and counting. And we're getting close, but we're not quite there yet. Give you a sense of it, we generate 140 distinct data products in the course of making all those steps come together to make those final images. So there's quite a lot to it, and we're working very hard so that you don't have to, right? So that we can do all this processing and deliver calibrated and background subtracted images that are useful immediately. Anyway, I'm sorry, that was a long-winded answer. In the longer term, yes, we'd like to see more of these things fly. But we don't yet know what we'll discover with Punch. So we'll have to see what comes up over the course of the next year before we know what we need to do next.
When's your
No,
scheduled phase E supposed to end?
Let's see, we have a 2-year mission that started last June, so we got about 15 months to go.
Okay. But do you already
But
have extended mission ideas?
we have ideas for how to continue. We're going to ask for a bridge phase to get synchronized with the NASA senior review process.
Okay.
But just given the amount of time it took to get the data in order, we'll probably still be working on the science when the prime mission finishes. The well, seeing CMEs propagating across the solar system like that is sort of like watching hurricanes from geosynchronous orbit, right? Before we had geostationary weather satellites, people tried to forecast hurricanes by looking at, their finger in the air, or they'd have a windsock or a collection of them. People would radio in air pressures from all over the place, right, and try and forecast storm propagation and hurricanes, and it didn't work very well. When we started launching GOES satellites in the late 1960s, everything changed just like that, because you could just track the storms, you could see them, and now we take that for granted. I think this is going to happen with punch-like instruments with space weather, right? That now that we have seen that you can see these things routinely and watch them propagate, we're not going to be able to give that up.
Without a doubt, yeah. I mean, especially with, a supposed human future in space, round the clock. Kind of want to know what's going on out there for sure.
Exactly.
All right. Well, we're up on the hour. I think I'm going to end the recording here. So thank you so much. This has been absolutely fantastic. I really thoroughly enjoyed this. And again, we'll be posting this on the Coffee's YouTube channel in the HelioHub playlist, so you can always review it there. But maybe we'll have some questions too after we end the recording. That sometimes happens. So let's see what happens there. But thank you again, Craig. This was spectacular, and best of luck with your continued engagement with Punch. I'm sure you're going to get some spectacular imagery that I'll be looking for in the news for sure.
Excellent. Thanks for the opportunity to speak to you.
Yeah. Phoebe, Claudia, any last words?
Just thank you so much for being here.
thank you.
Everybody was really excited to get to learn about more Helio missions, and this is one of the major ones right now happening, and getting to experience it in the moment is really exciting.
Excellent.
Yeah, a rare treat for us. All right.